this video, I will be walking through the complete implementation of a Connect6 game on ZedBoard from hardware block diagram all the way to the software running on the processor. The game is displayed on a mo monitor using VGA ports. So it is controlled through a ZyMouse which is located in the board. So let's get started with the block diagram. So here's the Vivado block diagram. At the so you can see here this is the main part of the block diagram. At the heart of it is the Zinc 7 processing system. So the PS side of the Zinc chip which runs our C application on ARM Cortex A9 processor. All the peripherals IP blocks you see here are connected to the PS via AXI interface. So next is the AXI interconnect. Like it is the bus fabric. It takes the master AXI port from the PS and fans it out to all the peripheral slave blocks like GPIO, the VDMA, and the custom ZyMouse IP. Think of it as the central highway connecting the processor to all the hardware blocks. Then the AXI GPIO block provides a simple general purpose output from the PS to PL fabric. In our design, this is the used to send a reset signal to the Connect 6 AIP core. The processor writes a 1 followed by a 0 to this GPIO to pulse a reset at the start of the every new game. Next is the clocking wizard. The clocking wizard generates the pixel clock required for video output. It takes the system clock as input and produces the precise clock frequency needed to drive a 1920 cross 1080 display, along with a clocked signal to confirm the clock is stable before the video starts. Next, you can see the processing system reset. So we have two process system reset blocks. One is 100 megahertz and another one is the 148 megahertz corresponding to the two different clock domains in our design. These blocks manages the proper reset sequencing for all peripherals, ensuring everything comes out of reset cleanly and in the right order. Next is AXI VDMA. So VDMA is basically video direct memory access. So it what makes the video output possible. It reads the pixel frame buffer stored in DDR memory and streams it continuously to the video pipeline. The PS writes game graphics into the buffer and the VDMA fetches it to the display at 60 frames per second without any CPU involvement. Next is AXI Smart Connect. It's above the AXI VDMA. So the AXI Smart Connect sits between the VDMA and the DDR memory. It handles the AXI protocol conversion and allowing the VDMA to efficiently access the high performance AXI HP port on the Zynq PS for fast memory reads. Next is video timing control. So you can see here the video timing controller. It generates all the synchronization signals for the display, horizontal sync, vertical sync, and the active video window signals. It receives the pixel clock from the clocking wizard and outputs precise timing that drives the AXI4 stream to video out block. So it streams out to video out block. So you can see it is above the video timing control. So the video stream to video out block takes the pixel data stream coming from VDMA and the timing signals from the VTC and combines them into a proper video output signal, complete with H-Sync, V-Sync, and the active video data, which is then sent to HDMI out connector. Next is the custom IP block we have created, like the ZyMouse IP. So the ZyMouse here it is. So the ZyMouse block is a custom AXI peripheral that interfaces with a USB mouse via PS2 style signal, tracks the mouse position, generates interrupts on movement and button press events, and stores the current X and Y coordinates in the register that the processor can read. This is how the player moves the cursor and moves stones on the board. Next is Connect 6 IP block, which is also a custom block we have made. So you can see here it visible as the RTL Mux block in the second diagram. Is the custom FPGA AI engine for the game. It communicates with the PS through VGA. The process sends the player's move coordinates over UART. The FPGA AI computes the best response and sends back its move coordinates. This offloads the AI computation entirely to dedicate hardware logic. So next is the X-Slice block. You can see here three X-Slice blocks are there. So the X-Slice block extracts specific bit range from wider signals for routing purpose. Next is the concat block, combines single bit signals into wider bit. Here it merges two 1-bit signals into 2-bit signals. And the next one is the constant block. It simply drives a fixed value onto a net used here to tie off unused inputs cleanly. So this is the total block diagram. From this block diagram, we have generated the system wrapper by right clicking on the BD file and create HTML wrapper. Then it will create the system wrapper. Then we will run the bit stream. First running the synthesis, then after synthesis we will run the implementation. After that we will run the generate bit stream. So here you can see that right bit stream is completed. Then next we have to export the hardware like this to software. Yes. Then we have to launch the SDK. Here the Xilinx SDK is open. So you can see here that it generates the system wrapper HW platforms, and we have to create the BSP files, and we have to create some source files to write the code and run on the FPGA board. So this is the game top.c. So this is the main application. The main entry points installations all the peripherals, the video pipeline, the UART for FPGA communication, the ZyMouse and the interrupt controller. It then enters a game loop, drawing the board, alternating turns between user and the FPGA AI, and checking for a win condition after every move. So you can see here that convert board coordinates to pixel center. This is the code for it. And you can see here it highlights all the six winning stones with the green outline. This is some features. These are some features that I have think. So you can see here show FPGA thinking on the left on green color and show, and these are the some features which I have added in the games, and these are the code for it. This is FPGA play. This is a user play one, and this is a show welcome. Like it shows the Connect 6 on the first while opening the game. The next one is video.c. So here it's like a video installation. The initialization video function configures. So this function configures the AXI VDMA driver, setting the frame buffer address and DDR, configuring the horizontal and vertical size to 1920 cross 1080 and starting the circular red channel so the display refreshes continuously from the frame buffer. So this is the code for it. So this code is basically for showing the output on the monitor. Next one is the ZyMouse.c code. Like it is the mouse driver. So the ZyMouse driver configures the custom mouse IP by writing to its AXI register, setting max coordinates, enabling interrupts, and registering callback functions. The moveback draws. So the moveback draws interrupts and registering callback functions, and redraws the cursor by saving and restoring the pixels under the pointer. Press callback converts pixel coordinates to board grid and places a stone. The next one is the Connect6.c. So this is the main game logic and the UART communication. So this is the Connect6 module. Handles the shadow board, a software copy of the game state maintained in a 2D array. The start game function sends a start command over UART to the FPGA AI, send coordinates and get coordinates, and handle byte level UART communication to exchange moves. Check game over, scans all rows, columns, diagonals to detect a 6 in a win row. So these are the codes for detecting left, right, or vertical ones. These are for getting coordinates and setting the coordinates. And next one is the graphics.c. So this is the graphics.c file. So it is about rendering. Like the graphics module draws everything directly into the frame buffer and the grid lines, the black and white stones, the cursor pointer, and the text strings like FPGA thinking or black turn and the winner announcement. Since the VDMA reads from this same buffer, any write is immediately visible on the screen. So you can see here that these are the columns for the board I have made in this code. And there are some header files which are supporting these .c files. Example like graphics.h for defining the colors of the game or video.h, or you can see the ZyMouse.h and Connect6.h. These are mainly important for running the .c files in the SOC board. Then you can program the SOC board by clicking Xilinx and program FPGA. So you have to upload the bitstream generated from the Vivado and keep it here and click the program. Then you can start with the build project. Here it will run the build project and run as launch on hardware system debugger. You can see here that the board has been connected to display monitor via VGA port. You can see the Connect 6 in the screen. Now I want to choose either black or white color for playing in the game. So you can see I have changing the mouse by clicking the buttons in this board. So center is for the clicking and rest 4 are for direction, changing the direction of the pointer. So now I am choosing the black color for playing the game. So you can see the board has been appeared in the screen with the 19 cross 19 squares. So now I am playing the first move. So here you can see that when I play the first move, only the one stone can be placed. from next move onwards the 2 stones will be placed in the game. That's the rule of the game. So you can see here that the FPGA is playing in the white color stones. So you can see here the in the right side black turn and the left side FPGA is waiting. So FPGA is waiting for my input. So now it's my turn to block the connecting the 6 stones. So FPGA is thinking other way to connect the 6 stones. So I am blocking that moves also. So you can see here that the last move is highlighted with the red color and the white one. You can see here in this one. So again I am playing 2 stones, placing here. So again the FPGA is thinking to connect in other way. So you can see here that the FPGA one, the highlighted green color. So now I am playing with the black color one. Sorry, not black color, white color one. So you can see here that the FPGA has already played on black stone. So now I am placing the white stone. 2 white stones here. So for every last move is highlighted with the red color one. So you can see the number of moves made by FPGA and your move also. So here you can see that the number of stones I have placed are totally 6. So your move is 6, and you can see here that the FPGA total stones placed are 7. So you can see that the FPGA move is 7. So it will calculate how many stones have been placed in this game. So you can see here that the highlighted one and green one. So again the game will restart from the starting. So you can choose either black or white to play again the game. Thank you.